So you've probably heard of RSA encryption, right? It's the magic that keeps your credit card details safe when you shop online or keeps your messages private. But have you ever wondered how it really works? Not the high-level theory, but how it actually runs on a computer. Well, today we're going to pop the hood and look at the clever engineering that turns this mathematical concept into a real-world tool. We're going to break this down by tackling 4 big questions. First up, what's the secret sauce that actually makes RSA secure? Then, if it's all about huge prime numbers, where do we even find them? After that, we'll get into the nitty-gritty of how computers can even do the crazy math involved. And finally, we'll see how RSA is used in the real world to protect our everyday data. Okay, let's kick things off with the big one, the question that everything else we're going to talk about is built on.
So what's the fundamental trick here? Why is RSA actually secure? What keeps our stuff safe from anyone snooping around?
You know, the answer is actually pretty elegant. It all boils down to this. Multiplying 2 huge prime numbers together is super easy for a computer. But going the other way, taking that massive result and trying to figure out the original 2 primes you started with, that is incredibly difficult. It's like a one-way street for numbers. Easy to go in one direction, but practically impossible to reverse.
And when I say huge, I mean mind-bogglingly big. A standard RSA number today is 2,048 bits long. That translates to a number with 617 decimal digits. Just to give you an idea of how big that is, if you tried to crack it by just trying all the possibilities, even with the most powerful computers on Earth, it would take longer than the age of the universe. Seriously. That's the computational brick wall that keeps RSA safe.
Okay, but wait a second. That brings up a really good question, right? If it's so hard to find the prime factors of a big number, how in the world do we find those giant prime numbers in the first place?
It kind of sounds like a catch-22, doesn't it? Like, if we can't factor them, how can we be certain we're even holding a prime number? Well, the solution is another bit of mathematical genius. Turns out you don't actually need to factor a number to know if it's prime. Instead, we use something called a primality test. You can just grab a huge random number, run it through this test, and the test will spit out a simple answer. Yep, it's prime, or nope, not prime. And you get that answer without ever having to find its factors.
Now this is where things get really practical. Engineers have a choice to make. There's a test called AKS that's, well, it's perfect. It's deterministic, meaning it will always give you the 100% correct answer. The problem? It's just way too slow. Then you have the Miller-Rabin test. Now this one is probabilistic. That means there's a tiny, infinitesimal chance it could be wrong. But when I say tiny, I mean the odds of it making a mistake are smaller than the odds of a meteor hitting you while you're listening to this. It's so incredibly reliable and it's fast. So guess which one everybody uses? Yep, Miller-Rabin is the workhorse behind pretty much all RSA key generation.
All right, so we've got our giant primes, we've built our keys, awesome, but now we actually have to use them. And that means doing some seriously heavy-duty math.
See, the math for encryption involves taking a number and raising it to the power of your key. But the key itself can be another one of those 617-digit monsters. If you tried to calculate that directly, the resulting number would have more digits than there are atoms in the universe, literally. So how on earth does a computer do that?
The trick is a super clever algorithm called repeated squaring. Instead of multiplying a number by itself a gazillion times, it does something way smarter. First, it takes that giant exponent and converts it to binary. Then it quickly builds up a list of powers just by squaring the previous result, like x squared, x to the 4th, x to the 8th, and so on. Finally, it just multiplies together the powers that match up with the ones in the binary number. And the real key is that it does all of this modulo n, which keeps all the numbers from ever getting too big. It's an amazing shortcut that makes an impossible calculation totally manageable.
Okay, but there's one more mathematical hurdle. When you're first creating your keys, you need to calculate your private key based on your public key. How do you do that efficiently?
You're not going to believe this, but the answer is an algorithm that's more than 2,000 years old. It's called the extended Euclidean algorithm. It's this incredibly efficient method that just so happens to be perfect for finding that private key. It's amazing, right? An ancient piece of math is what makes our modern digital security tick.
Okay, last section. Let's bring this all home. We've got all the components, we know how to do the math, but how does this all come together in the real world? Like when you connect to a secure website.
So here's the last big practical problem. RSA is what we call asymmetric. It's great because you can shout your public key from the rooftops, and that's fine. But it's kind of slow.
On the other hand, you've got symmetric systems like AES. They are lightning fast at encrypting data. The catch? You have to somehow share a secret key with the other person without anyone else seeing it. So you've got this trade-off. What's the solution?
Simple? We don't choose. We get the best of both worlds by using them together in something called a hybrid cryptosystem.
And here's how it works. It's really clever. Instead of using slow old RSA to encrypt, say, a huge file, your computer does this. First, it creates a brand new, random key for a fast system like AES. Second, it uses that super fast key to encrypt your file. Now, how do you get that key to the other person securely? That's where RSA comes in. You use RSA just to encrypt that one tiny little key. Then you send the big encrypted file and the tiny encrypted key over together. The person on the other end uses their private RSA key to unlock the little AES key, and then uses that fast AES key to unlock the big file. It's brilliant. You get the easy key sharing of RSA and the speed of AES.
So that leaves us with one final, pretty big thought. The entire house of cards that is RSA security is built on one single idea, that factoring huge numbers is hard. But what happens if it isn't anymore? What if someone has a massive mathematical breakthrough? Or what if powerful quantum computers become reality? If that assumption ever falls, a huge chunk of our modern digital security could break, almost overnight. It's kind of a wild thought, right? So much of our world is protected by this one, elegant, but maybe fragile mathematical problem.
Hey, if you found this dive into how RSA really works interesting, do me a favor and hit that like button, share it, and subscribe for more. We'll catch you on the next one. Thanks for tuning in.